Okay, let me just find. Okay. So thanks, Mark, and thank you very much for the invitation, and to the other organizers as well for inviting me to present my work on causal sets here to the Asymptotic Safety Seminar Series. Just to double checking, you can see my screen and the pointer, right?
Yes.
Yeah. Okay. So the content of the talk that I'm going to present today is based essentially in two works that we published last year. The first one was with Astrid Eichhorn and also Christopher Pfeiffer, who was a master student here in Odense at the moment. And the second work is also in collaboration with Astrid Eichhorn and also with Ludwig Fausten, who was also a master student here in Odense at that time. This is the outline of my talk. I will first give an introduction, and the idea is to give an introduction to causal set theory, but also try to motivate on why to build connections between different causal set, different quantum gravity approaches. In the second part of my talk, I will talk about curvature operators in the context of causal sets, and in particular of a novel construction of high-order curvature operators in causal sets. And then I will discuss how to use this these high-order operators to construct a discretization of the causal set action beyond the Einstein-Hilbert action. And finally, in the third part of my talk, I will discuss some explorations that we did using functional normalization group techniques in the context of causal set inspired scenarios. In particular, I will talk about an application of functional normalization group studies to self-interacting scalar fields in a causal set background, and show how we can use this to connect causal sets, a kind of non-locality scale that appears in the context of causal sets with an upper bound on the Higgs mass in a causal set scenario. Okay, so let me then start with a motivation on why to connect different approaches to quantum gravity. So the current status of our quest to quantum gravity is such that we have several alternatives. We have asymptotic safety, we have string theory, and many others. These different approaches, in general, they are based on very different assumptions. And generically, they are also based on different methods. And in general, they all face some kind of challenge. And typically, they also have different challenges between the approaches. What can be a challenge in one approach can be solved in another approach, and so on. Or they can also share some of the challenges. And the point of view that I want you to make in this talk, and that also motivates our work, is that the cross-fertilization between quantum gravity approaches can be very beneficial for the whole quest of quantum gravity. In particular, using ideas or methods from one particular approach of quantum gravity can lead to insights to overcome challenges in other approaches. Okay, and in this talk, we are going to do this by connecting two different approaches, causal set and asymptotic safety. And I guess that's the connection to asymptotic safety is the reason why I was invited to give this talk in this seminar series. And there are two kind of ways that we are going to do this connection. And the first one is exploring the idea that a causal set can potentially work as a kind of discretization method to define a notion of Lorentzian coarse graining in asymptotic safety. And the new step that we are doing here and that I will present in this talk is the construction of high-order curvature invariants in the context of causal sets. And the second way to build this connection is applying functional normalization group methods that are very common in asymptotic safety. And I mean, it's needless to say this to this particular audience. But the idea is to apply this to a causal set inspired scenario. And I will make more clear later why I'm calling this a causal set inspired scenario and not exactly a causal set scenario. Okay, so let me then give a basic introduction on causal sets. And before giving you a technical definition of what is a causal set, let me first motivate the basic aspects of causal set theory. What are the assumptions and why we use these assumptions in the construction of a theory of quantum gravity? So the idea is that causal sets is basically based on two aspects. The first one is that space-time has a causal structure. And the second one is that there is a fundamental spatial temporal discreteness scale. And the motivation for the first one is that space-time points, generically, they form what we call a partial order set or a pose set in a mathematical, in a simplified way. And the idea is that the pose set structure or this causal structure is a kind of distinguishing feature for Lorentzian geometries. If you go to any other signature, for example, you can go to a signature like a Euclidean signature or a signature with 2 times and 2 spatial directions. You don't have, you cannot define this feature of a partial order set. So this is really a kind of distinguishing feature that only appears in the context of Lorentzian signatures or Lorentzian geometries. And the second motivation is related to this theorem by Hawking, King, McCarthy, and Malamud. And I'm quoting this theorem here in a very loosey way. So the actual formulation of the theorem, it's a bit more rigor. It comes in a more refined language. But the important point, the important key message of the theorem is that a pose set or a partial order set is essentially sufficient to reconstruct geometry up to a conformal factor. This basically means that once you fix the causal structure of your space-time, you can essentially reconstruct all the geometrical information apart from a conformal factor. In other words, if you have 2 geometries that shares the same causal structure and they are related by a conformal transformation, then they are essentially equivalent in this language. And the idea now is, since this theorem that tells us that the pose set structure is sufficient to reconstruct up to a conformal factor, then in order to reconstruct the full geometry, we also need somehow to fix a volume, a conformal factor. And this is done by imposing fundamental spatial temporal discreteness. And the idea here is that this will fix a kind of fundamental volume in the theory. And with this notion, we come to the usual equation from causal sets in the causal set community, that space-time is essentially partial order plus volume. Okay? So now that we have the key aspects and a motivation for the key aspects, let me give you a bit of mathematical definition and actually define what is a causal set and how we want to formulate things in a causal set. So generically, the idea is that a causal set is a kind of, it's essentially a set with a relation that I will call precedes, and denote in this way here, such that the first assumption that we make about causal set is that given 3 points, and if the first point precedes the second point and the second point precedes the third point, then the first point precedes the third point. So essentially, this is what I have here with my example. So x precedes y, y precedes z, and therefore x precedes z. And in this way, it's quite redundant to add this link between between x and z. So I can just omit this in my representation of a causal set. The second assumption about a causal set is that given 2 points, if x precedes y and if y precedes x, then necessarily x is equal y, which essentially means that there is no time-like, no closed time-like curve. So in this sense here, if you follow transitivity, this would essentially implies that x precedes y and y precedes x, and this is something that we exclude from causal set. This is not allowed in a causal set. And the third assumption about causal set is that given 2 points, the number of points between these 2 points has to be finite. So here I have x and y, and I have a bunch of points y1, y2, and it goes on, such that they are between, in this causal notion, between x and z. And the idea is that this number here, the number of points between, in a causal sense, between x and z needs to be finite. And this is basically what imposes local finiteness in the theory, or in other words, this is the requirement of discreteness in the theory. Okay? So what we want to do is a theory of quantum gravity based on causal sets. This essentially means that instead of performing path integrals over geometries, I'm going to perform a sum over all causal sets. And of course, in order to do that, I need to specify what is my action over for a causal set, what encodes the dynamics of a causal set. And this is one of the points that I want to address with my talk, how to define such an action in a causal set. Okay, so, well, the example that I gave before for a causal set does not look like anything like a geometry. So just 3 points does not resemble a geometry. Generically, given a causal set, reconstructing a geometry is not a simple process. But given a geometry, we can reconstruct, or we can construct a causal set by something that we call a sprinkling process. And the idea of this sprinkling process is essentially you randomly throw points in a geometry. You do this according to a Poisson distribution because you want to keep Lorentz invariance of the theory. And the idea is that the way that you define the partial order between the different points that you sprinkle in a given manifold is essentially inherited by the causal structure of the geometry. So you have a manifold, you know the causal structure of this manifold, then you randomly you randomly sprinkle points in this manifold, and then you can define the a causal set by inheriting the causal structure from the geometry, from the manifold itself. And of course, the idea is that more than one geometry in principle can correspond to the same causal sets. And this is because in principle, in principle, they can differ by, they can have differences at scales smaller than the sprinkling density. So this process of giving a causal set, reconstructing the geometry, if you think in this reverse way, this is not a unique process. You can have different geometries corresponding to the same causal sets as long as they differ at scales smaller than the sprinkling density. Okay, the other thing important about this relation between causal sets and geometry is that not all causal sets come from geometry. So there are some causal sets that are what we call non-manifold-like. And one example is this kind of Kleitman-Horschel orders, or Ki orders, that are non-manifold-like causal sets. Here there is an example of a 3-layer Ki order. And one tricky, or one issue related to this class of non-geometric or non-manifold-like causal sets is that they essentially dominate, or they entropically dominate the set of possible causal sets. And therefore, just from the naive counting of what are the possible causal sets that we would have, it comes the natural question on whether they are or not suppressed in a classical limit. And concerning this question, I would like to point quite interesting work done in the last years, where they show that for at least a certain class of Ki orders, they are indeed suppressed in the path integral over causal sets. Okay. So now that we know what is a causal set, let me then move to propagation of particles or fields in a causal set background, and on how to define a causal set dynamics, because as we are going to see, these kind of questions, they are kind of connected in the way that we construct the causal set dynamics in a causal set theory. Okay, So the first question that I want to address here is how to describe propagating fields in a causal set. This comes with a warning, which is we know how to do this for scalar fields because, I mean, scalar is just a number defined in a given point, but we have no idea on how to do this for non-scalar fields. So we don't know how to define non-scalar fields. Could be vector field, could be a tensor field, a spinor field, propagating in a causal set. But let's restrict ourselves to scalar fields. So the idea here is that we basically copy what we do in a continuum spacetime. So a scalar field in a continuum spacetime maps point from a manifold to real numbers for real scalar fields. And the scalar field in a causal set maps point from a causal set to a real number. The idea is we want to define a dynamical scalar field. And if you want to try, I mean, if the idea is to copy what we do in a continuum space-time, then we directly have a problem. So in a continuum space-time, this is how we would describe the action for a scalar field. And the problem here is that there is a kind of no-go here. There is no tangent space to define derivative operator in a causal set. And this is very much related to the reason why we cannot define non-scalar fields in causal sets. But there is a way out. So in a continuum limit, we can also rewrite this action in this way here. So instead of writing as derivative, now we can write as a field box field, the Lambertian box field. And since there is no vector anymore, so there is just the Lambertian here, which acting on a scalar gives another scalar. Now we can define the action in terms of something that is meaningful in a causal set. And the idea here is we can define this box operator in a causal set, which is also called the B operator in the causal set community, as a kind of sum over layers, over different layers. I mean, let me try to explain what is the idea of layer here. So in this drawing here, the idea is that this black point in the top, this would be the point X, where I'm evaluating my scalar fields. And points in red here, they correspond to first layer. So they are essentially the set of first neighbors in a causal sense, from the point X. Then blue, they correspond to the second layer. So essentially the second neighbors in a causal sense. And then it goes on. In yellow, I have the third neighbors, and in black again, I have my fourth layer, which corresponds to fourth neighbor. So the set of points essentially for a given layer, this essentially counts how many points I have to jump until you get to the original point. So essentially from the first layer, I just go directly to the original point. From the second layer, I have to jump over one point and then go to the next layer. And then I reach the original point and so on. So this is, I mean, a kind of covariant version on how we define, or a covariant Lorentzian and covariant way on how we would define a derivative in a lattice. In a lattice, this would essentially come from the finite distance operator where we sum over, where subtract first neighbor and so on. I think there is a question.
Yes. Hi, Gustavo.
Yes.
I'm wondering what these coefficients are in front of these sums, the 9, 16, and 8.
That's a good question. So there is no intuitive way of explaining from where these coefficients come from. The idea is that you have to do a long calculation, but you fix this coefficient by demanding that once you take this operator and you average over sprinklings, and you take the continuum limit, so you send the discreteness scale that was actually supposed to be to 0, not to infinity. When you send the discreteness scale to 0, then you recover the D'Alembert operator. So there is no intuitive way of seeing that I know at least. This comes from the result of this calculation. And I also have to mention that if you do, I mean, this is for sprinkling over 4-dimensional Minkowski space. If you do this for other dimensions, you have different coefficients here. Okay.
Okay, thank you very much. Cheers.
But it's a posteriori
Yeah,
thing that we have to see.
right.
So, well,
Cheers.
with Gabriel's question, I already advanced over the next point that I was supposed to say, that the idea is that the way you see that this corresponds to D'Alembertian operator is by averaging over sprinklings, and in particular, if you average over Minkowski sprinkling and take the continuum limits, then you recover the D'Alembertian operator in a continuum limit. Okay? But actually, what is interesting about this construction, or one of the interesting aspects of this construction of the D'Alembertian in a causal set scenario, is that the causal set D'Alembertian actually encodes more geometrical information. This encodes more than just the D'Alembertian operator. And again, this was supposed to be L going to 0, so discreteness scale going to 0, sorry for the typo. And the idea is that now if you average this object over sprinklings over pseudo-Riemannian manifolds, so not only on sprinklings on Minkowski, now besides the D'Alembertian acting on the scalar fields, you also get another contribution that encodes the scalar curvature of the manifolds. This has been verified numerically and also analytically. And the idea is that with this result here, we can now, this is a way of defining something that we call the scalar curvature operator in a causal set. So the point here is, despite no Riemann tensor, there is no tangent bundle to define tensors, so we cannot define a Riemann tensor in a causal set. We can still define something that corresponds to a contraction or a trace of the, a trace of the Riemann tensor, right? So we have to first go to Ricci tensor, and then we go to scalar curvature. So despite no Riemann tensor, we can still extract some information about causal set curvature if we'll focus on scalar curvature. And the idea is that this relation here would essentially give the definition of what we call scalar curvature in a causal set. And now that we have a scalar curvature in a causal set, we can try to understand how we can construct the dynamics of a causal set. And the idea is we start from the dynamics in the continuum limit, so just the Einstein-Hilbert case. And since now we have curvature or scalar curvature defined in the causal set, then we can construct a discretized version of the Einstein-Hilbert action in a causal set. And this is what people call the Bennings-Casadolker action. And well, in principle, we can write in terms of this B operator, but there is actually a nicer relation in terms of this. N here is the total number of points in the causal sets. And then we have N1, N2, N3, and 4, and they correspond to K order or K plus 1 elements inclusive orders in a causal set. So this is an example of what is 2 order. This is a 3 order. This 2 contributions here, these 2 chains here, the diamond of the chain here correspond to a 4 order, and so on. So the idea is this kind of intervals that contains a certain number of elements, and they are causally connected. Okay, so now we have an action for a causal set to describe the causal set dynamics. So what we can do about this? And one thing that we can try to do is to connect this to asymptotic safety and try to use this to assist the asymptotic safety problem. And in particular, assist with one of the challenges that we have, which is related to the fact that in the asymptotic safety community, the main tool that we use is the FRG. The main tool is the FRG. And apart from very few exceptions, most of the FRG works on asymptotic safety. They probe Euclidean asymptotic safety. And more than that, we also have the issue of uncontrolled systematic errors because of the use of truncations and so on. And the point here is that interaction with other approaches, this can help us to overcome this challenge. In this sense, I should note that there is a lot of effort on searches for asymptotic safety from the lattice community. in particular for Euclidean and causal dynamical triangulation. And the key idea here is to also try to search for asymptotic safety from a causal set perspective. And the point here is we can use, so since we saw that there is a way to take continuous action and discretize this in a causal set manner, then we can use this kind of discretization to explore the phase diagram of causal sets, and in particular, search for asymptotic safety in the form of a second order phase transition. And if we find such a phase transition, then we can ask questions like, does it correspond to the same universality class that we see for an FRG calculations, for example? Let me briefly mention the state of the art on this direction. So by now there is some works where people explore Monte Carlo simulations using the Beni-Casadal action, both in 1+1 and 2+1 dimensions. And they see evidence for a phase diagram with a kind of phase boundary. However, there is also evidence that this phase the phase boundary corresponds to a phase transition of first order. So far there is no evidence for asymptotic safety from a causal set perspective. And the question that we want to raise here is whether this is indeed a feature of the causal set phase diagram, or is this an indication that the Beni-Casadal is not sufficient? And in particular, concerning the last remark, we can take some inspiration from FRG results. And here I would like to point out that there are several FRG studies that shows that the Einstein-Hilbert truncation does not include all relevant operators at the ultraviolet fixed point. In particular, all the results in this direction, they point towards the idea that we need to include some combination of curvature square operators in order to include all relevant operators at a UV fixed point. So the natural question here is of course, is it possible to, the first question is, it's possible to introduce such high order operators in a causal set action? And if so, how does the causal set phase diagram looks like if you extend the Beni-Casadal action to include high order operators? And in this part of the talk, I want to focus on the first attempt or the first step to answer this question, which is construct the kind of operator and the extended Beni-Casadal that we would like to use in order to study the phase diagram in causal sets. And first of all, what are the kind of operators or what are the kind of terms that we would like to include in a Beni-Casadal action to study the phase diagram? And the idea here is the extended Beni-Casadal action, let me call it this way, from this FRG motivation should include at least curvature square operators. In this talk, I will focus on on the R square, just the scalar curvature square. And I want to actually raise the point here that, in principle, we can think that the other operators, they are not possible to construct because they are built in terms of tensorial quantities. But we have been discussing, Astrid and I, and we think that there is a way to extract this kind of operators as well. But this is still, an idea that we are starting to explore, and we don't have any concrete result at this moment. So let me focus on the scalar curvature square. Well, the basic idea is we can essentially construct the R square operator by acting with B operator twice. So essentially, I define B square as B acting on B of phi, just using the definition of B acting on something. I get this expression, which I can expand a bit more. And the structure of the B square operator looks like this. And in particular, I have some terms here that's, well, I have my scalar field and then a sum with some coefficients of sum over one layer, essentially. So it can be first, second, third, and fourth layer. But then I also have this kind of double sum over layers. So I have a sum over layer and a sum over layer in the past of the previous layers. And we believe that this is one of the reasons that we found some challenges on numerical simulations when we try to go beyond the analytical implementation of this operator. Well, but I mean, without going into details of the proof, the idea is that from this definition, you can show that if you take the average over sprinklings on non-Riemannian manifolds and take the discreteness scale to 0, so again, sorry, there is a typo here, then in the continuum limit, essentially this corresponds to this expression here, which now involves the Lambertian square acting on something and other contributions. And once you, I mean, the idea is that now you can extract this particular combination. So you can extract R square minus 2 box of R, essentially by setting the scalar field to be a constant. You can even generalize this to higher orders. So the idea is that, I mean, essentially you can define Bn in this kind of recursive way. And from this recursive definition, you can work out a kind of recursive proof, or I mean, a proof by induction that taking the average over sprinkling and the continuum limit, Rn can be obtained by taking this particular average and limit, and then you have to subtract a bunch of other terms. So in this construction, you cannot, it's important to emphasize that in this construction, you cannot actually isolate R square or R to the power n, but you always have this kind of combination with other operators. Well, once we have now a generalization, so we have something like R square, or actually R square minus something else. Now we can construct an extended Beni-Casadolker action. And the idea is that the extended Beni-Casadolker that we can construct is essentially a discretization of this Einstein-Hilbert plus high order terms action. So I have the Einstein-Hilbert term plus a curvature square minus a boundary term in here. The discretization looks like this. We can recall that the Beni-Casadolker action corresponds to a sum over causal intervals or causal orders. And we can ask whether we can also write this kind of extended Beni-Casadolker action in terms of these causal orders. And the answer is almost. Because now, I mean, the part of the operator that involves just the sum over a single layer, they can be rewritten in terms of this nk, which corresponds to the number of causal orders. But now we also have this nkl, which now is the number of inclusive stacked orders. So we had to extend this notion of orders, causal orders, to these stacked orders with k plus 1 and l plus 1 elements. So the idea of stacked order is essentially, so for example, here you have a 2 order, a 4 order, and then you stack one on top of the other, and then you have this 2, 4 order. And an open question is whether this kind of extended Beni-Casadolker action, whether this, or how the phase diagram of this extended action looks like, and whether this exhibits a second order phase transition or any kind of phase transition. But this is still unexplored territory. So let me move to a slightly bit direction, a bit different direction now. And let me just go back to the point of propagation of fields in a causal set background. So the idea is I want to study how a causal set background impacts self-interactions in a causal, of a scalar field propagating in such a background. And the starting point here is this work by Aslanbehi, Sayavani, and Sorkin, where they show that if we start from a causal set action, or for the action of a scalar in a causal set background, and if you restrict yourself to sprinklings over Minkowski-like backgrounds or manifolds, Then you can write this kind of effective action in terms of Fourier modes, where this f of p essentially corresponds to the spectrum of the causal set D'Alembert in this class of sprinklings. This has this kind of nasty expression here. So a lot of things that we did had to do was done numerically. But the one important point that I should emphasize about this expression is that now I have this scale rho, which corresponds to a non-locality scale instead of the discreteness scale. This is no longer the discreteness scale from before, but it corresponds to a non-locality scale. And the idea is that this kind of non-locality scale, they appear in the construction of causal set D'Alembertians in order to tame large fluctuations that you get from averaging over sprinklings. So the kind of picture that we have here, if you think about the different scales that we have in our problem, is we have, below the non-locality scale, essentially we have a quantum field theory with standard propagators. So the scalar field would just be scalar, box, scalar, where this box is the usual D'Alembert operator. We have this intermediary region here where the causal set, with this causal set inspired propagator. So in the middle here, we have this region where we start to see non-localities due to the causal set structure. And then once we go to high energies, we enter the discreteness scale regime. And the idea is that at this regime, quantum field theory breaks down anyway, and we have to replace by another formulation, which is a proper causal set formulation. To make sense of an FRG study of this, we have to consider a kind of Euclideanized version of this causal set scenario. And the idea is essentially, okay, we want to apply FRG method. So we want to define mass shells in a Wilsonian way. And this would basically make sense in or to make direct sense of that, we need to go to a Euclidean scenario. And that's a quite important caveat in our analysis, that essentially we do this by defining this kind of weak rotation for this function f of p squared. And this was a very naive weak rotation. So this is consistent with the IR limit of this function f of p squared. But we didn't manage to do any rigorous check on whether this weak rotation makes sense or not in the full regime. So for this reason, we call this a causal set inspired scenario and not exactly a causal set scenario. So there is this kind of, there is this kind of caveat that we need to have in mind in the results that I will present here. So from that, the idea was to extract the flow of quark couplings of a couplet lambda using the FRG equation. So there is also the hypothesis that the background, the causal set background, changes only the propagation of the scalar field, but not the vertex. This is also kind of strong assumption. Using standard FRG techniques, this essentially corresponds to, computing the flow of such a coupling essentially corresponds to computing this diagram here, where now the propagator comes with this f of p squared, which comes from this causal set inspired scenario. The results already of the integrated flow involves this function f, which looks like this. So I have a regime here below z equal 1, and z equal 1 corresponds to the point where the renormalization group scale is the same as the non-locality scale. So below the non-locality scale, we have the logarithmic running. So as expected, we recover the standard result from standard QFT of a scalar field. But above the non-locality scale, we see kind of strong effects coming from non-locality. And in particular, we can see how these kind of strong effects affect the existence of a Landau pole in this RG equation. And the first thing is that including such modification from a causal set inspired scenario still leads to a Landau pole in the UV. And more than that, here I would like in particular to focus in this region of the plot, which is the region where we have small infrared values for the quartic coupling. And we see that even if you make the infrared value for lambda very small, you still have, you still get a Landau pole right above the non-locality scale. And this is quite different from the standard logarithmic running. So here in the dashed lines correspond to the situation where I don't have any causal setting-inspired modification. And here we see that if you make lambda sufficiently small, then you move the Landau pole to high energies. And here it seems that it's not the case. So even if you make lambda 0, lambda in the infrared sufficiently small, you still have the Landau pole right above the discreteness scale. And one possible consequence of this is that we can no longer have a larger separation between the non-locality scale and the discreteness scale. And I want to emphasize here that this separation is quite kind of required from the construction of the D'Alembert, because this large separation is something that you need in order to tame large fluctuations over when you average over sprinklings. And it seems, from this result here, it seems that it's perhaps not possible to get this large separation. Okay, so the last point of my talk is connection between these previous results and the Higgs mass. And the idea here is that, assume that you go through a spontaneously broken phase, then you can relate the mass of a scalar field or the Higgs field with the vacuum expectation value. And in particular, if you impose that there is, that the theory should be valid up to the Landau pole scale, essentially you can translate this into a kind of upper bound on the scalar mass, where this lambda of, this should be, instead of k lambda, this should be k Landau, where lambda is a function of the Landau pole scale. And this essentially comes from inverting this expression that we obtain here. And in particular, plugging the results that we found from the running of lambda, essentially we can relate the, we can infer a kind of upper bound on the scalar, on scalar mass, or in particular, the idea here is that this is an upper bound on the Higgs mass. Of course, that this also comes with some extra caveats. In particular, we are not considering any extra degrees of freedom that usually couple to the Higgs field. So standard model also have, also exhibit interactions between Higgs and other degrees of freedom, and we are completely neglecting that. And here we are just treating the vacuum expectation value as an external parameter, so there is no investigation on the flow of the scalar mass and so on. But assuming that this caveats does not change too much the results, this is the kind of final picture that we have, where here we see an upper bound. First of all, we see an upper bound on the Higgs mass as a function of the Landau pole scale. And in particular, we see that, so for this black line here, this is essentially the case where the discreteness is, or the non-locality scale goes, this row goes to infinity. So we move the non-locality scale to infinity. And we see that comparing this black line with the other lines where we have finite non-locality scale, essentially we see a very large difference on the upper bound of the Higgs mass. So, especially perhaps this plot here on the right is a bit more appropriate to understand what's going on. So especially if you want to have, so for example, if you focus on, let's say, gap between the Landau pole scale and the non-locality scale with order 10 to the power 3, essentially this restricts a lot the upper bound on the Higgs mass. It restricts a lot possible values on the Higgs mass. And assuming that since we want the upper bound on the Higgs mass around 100 GeV or so, I mean, of order of magnitude of 100 GeV, essentially the only possible ratio between the Landau pole scale and the non-locality scale is the one here in the top, where we have ratio 1. So the Landau pole scale is exactly at the non-locality scale, which again, Landau pole scale is the scale where we expect that new physics becomes relevant. So that we would expect that would be where we would expect that the discreteness assumption kicks in. And here we see that there is no separation between this new physics scale and the non-locality scale from causal sets. With this, I would like to enter my final remarks. And in this talk, I tried to express the point of view that the cross-fertilization between quantum gravity approaches may lead to new insights. And the idea is that challenges from a given approach can be solved from ideas and methods that are common in other approaches, in other quantum gravity communities. And as an example, we took the connection between causal sets and asymptotic safety. And the first idea here was to use the point, was to explore the point of view that perhaps causal sets can help us to probe Lorentzian asymptotic safety. And the first step here was to construct a causal set action, including all the relevant operators that we expect from usual or from most of the FRG studies. And the second, I mean, there are some outlooks here, some things that we would like to explore in the future. And one of them is the obvious idea that we should, I mean, using this extended Bennett-Casadolk reaction, we would like at some point to investigate the phase diagram with this extended action. And the second point that we would like to investigate in the future is how to construct, and if it's possible, and how to construct other curvature invariants from causal sets. And in particular, I think this is indeed possible with some modifications on the method, or I mean, and the sum over layers, let's put it this way. And the second example was related to using FRG methods that are common in asymptotic safety and apply this to causal set inspired setting. And in particular, we found that from this, I mean, under several assumptions, there is a connection between the non-locality scale and an upper bound on the Higgs mass. And one outlook / question that I would like to emphasize from here is whether we can actually have a large separation between the non-locality scale and the discreteness scale in causal sets, because this is, I mean, our result points that no, perhaps it's not possible. And this would have, I mean, quite strong implication on how the causal set is, the causal set D'Alembertian is implemented in practice. With this, I would like to thank you all for the attention.
Let's all thank Gustavo for a very nice talk.